In our time domain analysis using root locust, we would often design to specifications such as damping ratio, settling time, natural frequency. In frequency domain, the specifications are sometimes expressed a little bit different, but they can be related back to time domain specifications. 4 common frequency domain specifications are phase margin, maximum gain, bandwidth, and gain margin. Let's look at those one at a time. The phase margin is related to damping ratio. Phase margin of somewhere between 60 and 90 degrees gives you a damping ratio of about 0.707. A phase margin of about 20 degrees gives you a damping ratio somewhere around 0.1. There's not a direct one-to-one correspondence, but the smaller the phase margin, the smaller the damping ratio. And once you get past a phase margin around 90 degrees, then you're looking at damping ratios of 0.8 to 1. Occasionally, design specs are given in terms of maximum gain. Maximum gain is related to damping ratio for damping ratios that are less than 0.7, and the relationship is given here. Maximum gain is the maximum gain value for the closed loop Bode plot. So if the system looks like this, we've been doing Bode plots just for G. If you want to use the MR maximum gain specification, then you need to look at the transfer function of the Bode plot from here to there. If you're using the SISO tools, you can just turn on the closed loop Bode plot function and you'll be able to see the maximum gain right off of the figure. The third parameter that you're sometimes asked to design towards is gain margin. Gain margin is just related to the overall stability of the system. Usually the larger the gain margin, the better the stability. The gain of a system is often a parameter that you don't have a good handle on. So you might have a plant and you know about what the dynamics are, but you're not exactly sure what the gain is. So if you have a control system with a large gain margin, that means that you can have lots of uncertainty in the gain of your plant and your system will still be stable. The final parameter is bandwidth. Sometimes bandwidth is specified closed loop and sometimes it's specified open loop. The definition for bandwidth is given a Bode plot. Bandwidth is the frequency that corresponds to a minus 3 dB gain, where this is dB and this is the frequency axis here. Roughly speaking, in terms of the poles of a system, this is approximately equal to a system pole. And we should realize that from our approximation of a Bode plot, that the breakpoint is at the pole of the system, and that is approximately where the bandwidth of the system is too.